right, let's continue proving the remaining parts of theorem 6.55. So let's see. So in the last clip, we took care of A and B and C. So let's begin with D. Okay. If we look at an element V decomposed according to the orthogonal breakdown, then V minus the projection onto U of V is going to be V minus U. But V minus U, just by this identity that we began with, is equal to W. And by the decomposition, W is in U perp. So that does that one. For part E, let's see. So if we apply the operator twice to V, and I'm just using the same notation. So in other words, I'm taking this V to be U plus W here. So then that means that this part, PU applied to V, is going to be U. And now U lives in U. By the way, we defined the decomposition. So when I apply P to it, nothing happens. And so that was by, I guess, B. And this is the same thing as the projection to U of V. So that gives us our result. Then, let's see. Again, for V broken down according to the decomposition, if we look at the magnitude of PUV squared, then this is the magnitude of PU of V is just U. So we've got this one. And now if I take this number and I add a non-negative thing, it can only get bigger. So here's the non-negative thing I'm going to add. And now notice that U is orthogonal to W because we've got U in capital U and W in capital U perp. So this is equal to the magnitude of U plus W squared by Pythagoras. And then this is, of course, magnitude V squared. So now you just take square roots of both sides and you have this identity. All right, last part. So if we've got an orthonormal basis of E's here, then we can write V as the sum K equals 1 to M V against EK plus and then the other chunk. So whatever it needs to be. Right? Then by the decomposition here, we know that we have this part is in U, since the EK's form a basis. And then we've seen that this part here is going to be the orthogonal complement of that chunk. So when we apply P to both sides, then we're just going to pick up the part that's in U. There we go. And that's it. Well, there's actually one other last little thing, just sort of a side detail. I just wanted to point out that we're only doing projections in the finite dimensional case because we're doing them in terms of a basis, but projections actually They work in the infinite dimensional case too. They can just be a little bit harder to write down. But so for example, if we look at the continuous functions on the closed interval from -1 to 1, or actually more generally just from -a to a, so any symmetric interval around the origin, then this actually breaks down into an orthogonal direct sum between the evens and the odds, using the usual inner product here, where the inner product of f and g is the integral from -a to a of f of x, g of x, dx. And I guess actually here, let's work with real valued functions so we don't have to concern ourselves with the conjugate. So we've got this one. And you can even write down a formula for the projection. So the projection onto the evens of f, this is f of x plus f of negative x, so that's like the flip of x, of f, divided by 2. And then earlier I gave a homework problem where I denoted this as the even part of f, like that. But it's actually, you can think of it as the projection to the subspace. And then you've also got the projection to the odds, and the projection to the odds is f of x minus f of negative x. So you subtract its horizontal flip and divide by 2. And so earlier I called this the odd part of f and denoted it with a subscript O.